Yeah, hello. So today I want to talk about input ranges in C++ and techniques for production usage. So this came out of Silkworm project where we started using input ranges. And by input ranges, I kind of mean the ranges that read from files or databases or maybe networking. So it's not gonna be talking about like fixed collections like vectors or like in-memory structures, but mostly like sequential one by one kind of reading. So I/O kind of operations. And how to apply this std ranges library in C++ to that task. This is the plan of the talk. So I'm gonna talk about motivation, like why we want this, and then some basic definitions, but it's mostly gonna be covered by some other talks. So I'm gonna just quickly repeat what we need to know for this one. Then I'm gonna talk about creating custom views, then some debug techniques, then about zero copy data, and then conditional logic as well. So let's start with motivation. So first I'm gonna talk a little bit about history of the ranges library. So because some people might say, okay, it's C++ ranges. It appeared in C++ 20 standard, so maybe it's from 2020. So why do we care about it in like 2025? Already, like there's so many talks, so many documentation and presentations and blog posts on that, but apparently not. So apparently it's a long way to production, like from the experimental prototype. As you can see, it's been like 6 years to the standard. But then after the standard is published, it was published like in December, then in the next year GCC release and MSVC released their implementation. But okay, once the compiler, like let's say once the GCC is released, it's usually the main compiler on Linux, then it's not enough for production, because for production you probably want to be based on stable Linux distributions, and stable distributions, they came only like 2022 and 23 with support for ranges. And then a lot of developers these days, they use macOS with Xcode. They use Clan compiler from Xcode, and Clan team, they procrastinated 2 more years to completely implement, fully implement this ranges standard. So kind of at the end of 2023, we might say that yes, now we have all our developers and all our production systems, the library is rolled out everywhere and it's widely available as a part of standard library. Yes, you could use different libraries and experimental versions of compilers or libraries before that date, but like this, there are some other talks about that, and this is mainly about standard libraries. So there were like in when we started the project, like in last year 2024, we basically were in this state where, okay, it's available, let's try to use it. But one other thought here is that in C++, it seems it comes in order, like from idea to production, you see it's something like 10 years, but even from standardization to like fully being available for production, it's maybe 3-4 years, something like this. So this number varies between different languages, but yeah, for C++ it seems like it's on this slower end of the spectrum. So why do we want to use ranges at all? So we needed to implement something like this. So this is kind of the API that we want from our database engine or storage engine. We want to submit queries which have selectors based on like keys, timestamp, and we want to also vary by, we have like ascending or descending order, and then we want to limit the number of results in the result set, and also we want to paginate, so we want to split the result into chunks of a given size and then paginate. And to that nature, like it already seems kind of like, okay, we kind of need some data streaming API with support for like filtering and ordering and pagination. And also we knew that so this API we needed to implement. It was a part of Aragon project. So in Aragon project, it already was based on kind of a range API, but written in Go. So you can see there's a library called stream, which contains like range iterator with some next and has next, and some combinators like union and other combinators which work in a one-by-one iteration fashion. So yeah, so like performance-wise, maybe it's faster to do page by page kind of queries, but we knew that it was already done on this one by one level, so it was kind of good enough. And then we thought, okay, maybe ranges is a good candidate. Like why reinvent a wheel? Why like create yet another kind of iteration API? Let's try to use ranges. And this is kind of how the query pipeline might look like. So it consists of stages. It starts from this original range, and then it has it combines the latest stages with this pipe operator, kind of like Unix pipe. And it has something, yeah, it has various operations which are called views, which can be like transforming the data, it can be filtering. So in this case, it starts from some database cursor start, and then each record it has a key value and the timestamp, and then the first transform it extracts just the key and the value. Then the unique will produce a sequence with all the keys being unique, so it removes the duplicates. It does it by comparing keys, removes the duplicates, and then it uses take while to only keep iterating until a certain final key, like the maximum key, and then it will, for each key and value, it will decode the raw bytes into actual domain specific objects. Is that clear, more or less?
Yeah, makes sense.
Yeah.
So far.
So this is kind of what we aspired like to implement using ranges. It seemed possible, but then we found a bunch of like problems and a bunch of things we had to learn, and this is what I'm gonna be talking. So first, let's start from some definitions. Like there's this good talk by Simon Toth about what is a range. So I refer to that in the notes in the video description, and you can watch. I recommend to watch that, but it's basically defining a range as kind of a pair of begin and end, and then talks more, gives some examples. Here I'm just gonna reiterate on how ranged iteration works in C++, and it's on the top you see the ranged for loop, which can have anything, like it uses vector here, but it can be any collection, so collections are called range in this case, ranges, and it can have any range, and this syntax form, it will do kind of what you expect, so it's kind of a for each loop. And this loop actually expands to this thing on the bottom, so it calls begin method and end method, and it produces this thing called iterator, which supports ++ operation, and it supports a star operation for dereferencing. And this supports comparison with an end iterator, which is called the sentinel also. So this bottom form was available since the previous versions of C++, and now like it's generalized to be a range iteration. But so now you can see that in order to implement a custom range or a custom view, basically you will need to support this begin, end, and you will need to have an iterator which has these operations. Then it will work with, it will be compatible with the range for loop, and it will be compatible with the range API. Also, like to restate that it's this new range model is compatible with the old iterator-based model. You can always compare between the two. So if you have a range, you can just, like in this case, reader is a range. If you have it, you can always get begin and end iterators as by calling begin and end. And you can, having two iterators, you can use something called subrange to construct back a range. So it's a helper to come from iterators to ranges. The name subrange is a bit misleading because it's not really a subrange, but it's really just a constructor in this case of a full range. And the bottom example, it shows that actually, like, you don't even need like the end range, the end iterator, or the range itself. You can just have a single iterator and use something called default sentinel to act as an end iterator, as long as your iterator kind of supports this, which is kind of a nice thing. And another part of the picture is views. So how it differs from ranges. So back to this example. So the range is this first line, and then all the other lines in the pipeline, they are views. So there are different definitions of a view, but I would say that the primary characteristic is that the view is something that is composable using this pipe. So yeah, different people say that it's, for example, a lightweight or something to that nature, but actually it's not really true that it's lightweight, but it has to be combinable using pipe operator. And it does that using something called range adapter closure object. It's a helper object to help this form this combination using pipe. And it has to be kind of separately implemented. So as a result of combination, you get actually what's called a view. So yeah, so once you start trying to use std ranges library, you quickly find out that the views that are in the standard in the C++20 is not enough. You most likely need some views from C++23 standard, and also you need some custom views. So right off the bat you see like it's very limited, like it's not fully support, like you cannot just use the standard library like only for very simple cases. So this is the list of kind of views that we had to implement. So concat and own in view are from C++23 that we had to backport, and there's merge views, which basically take several ranges and combine them as a single stream. And there's the cache in view, which is available in ranges v3 library, but not in the standard, and it's also a kind of nice utility. So how to create a custom view then? So this is the first part of the boilerplate, and there's a lot of boilerplate code you need to add, but so first you need to inherit from this thing called view interface, and provide it uses CRTP, what's called CRTP. You pass a type of yourself kind of, and it's a bit magical, but it's something you just have to add. Then it has a default constructor, so it's again a part of a boilerplate, even though it's not really used in practice, maybe not in the code that we have, but you have to have it, otherwise the code will not compile. And it adds some extra limitations to the types you use. And then you need to implement your begin and end, because view is basically a range with some extra features. So like I said, it's view is a range which supports combining with other views and ranges. So you need to implement begin and end, and in this case it just uses it relies on some other iterator from vector, but most of the time you will have your custom iterator here, so you will have to implement a custom iterator class. I'm not going to cover how to do it in this presentation. You can find a lot of material about that, but basically coming back to this, like you have to implement a class which supports getting the value, so it supports the star operation, and it supports going to the next element using the plus plus operation, and it also needs to support comparison to the sentinel to know if the sequence is if the iteration is over. Is that clear?
Yeah, makes sense. And the pipe operator that is implemented by the view. So I saw you have like one
Yeah, I have a
view
slide about
interface.
this. So yeah.
Vector. Okay, I see.
Yeah.
Okay, cool.
Yeah, so this is a detail about this dereferencing operator. So this is how the dereferencing operator looks like. It's again a boilerplate kind of you have to add. The special thing about input ranges, as opposed to like ranges that represent, let's say, a vector, is that those input ranges, they when you read some data, there's no other place, there's no other good place to stick the data other than to put it in the iterator itself. So there's no like storage for the data other than the iterator. So basically the iterator, it owns the data in a way, and it means that you put this value inside the iterator, and when you dereference it, you need to return a reference to this data, to this value. But for some reasons, the concepts that in the standard library that define the ranges and iterators, they want your iterator dereferencing to be const. So they want it to be, they want iterator to not modify let's say the container or the values. But in this case, if you define it as const, then the reference you return, it also has to be const. But for the purpose of this kind of use case, and I'm going to be talking about it in the next chapter about zero copy, we want to achieve zero copy. So we actually want to move, instead of copying the value as we read it from the iterator, we don't want to copy. We want to actually move it forward through the pipeline and avoid copies. And when we move it, a move operation, it's kind of a write. It requires a write access, because when you move, you sort of reset. As you move the value out from the iterator, you sort of reset the value inside the iterator, so to say. And that's why it cannot be const here. So there's a contradiction. So this is one solution is to use, one hack is to use a mutable attribute, but there might be other solutions, maybe to use some shared pointer buffer or something like that. But this was the kind of the easiest. So this trick. Then another point, when you implement comparison of the iterator to your sentinel, this is kind of a typical way to do it. You kind of have to define all the four versions. You see it's equal, not equal, and also arguments in the reverse order. Otherwise, some compilers complain. And it's actually quite nice. It works. So basically, equal returns true if the iteration is over, and not equal returns true if the iteration is not over. So you can think of those operations as just, so not equal basically means has next. In other API, you might see this as a has next, and equal it means like has ended, something like that. So it just returns a boolean if it's true, if it's ended or not ended. So the sentinel, as you can see, is not really used. It just acts as a way to like resolve which function to call here. So as a argument dependent, as an overload lookup procedure, it finds which method to call. And this is to your question, how to implement a pipe. So there's actually no magic to implement a pipe. You need to implement it like manually. Well, actually there is a magic. There are facilities how standard library itself internally implements pipe for different views, but this is internal to each compiler, so it's not standardized, and it's specific to the compiler. So if you use only a single compiler, yes, you can try to reuse that logic from there, but so maybe it's instead of like inheriting this view interface, you inherit some, let's say, GCC specific interface, and you get this pipe for free. But typically, you like, if you want to support cross compiler kind of compatibility, like this is the easiest way, and it basically does exactly what is on this picture. So this closure object, it needs to support constructing from a range, and it needs to support range, pipe, and this object. So this is exactly what this code does. It declares this caching thingy as this helper object, and this helper object, it implements constructing from a range, and it returns a view, and it implements piping a range into this helper objects by calling this first method. So it's kind of again a boilerplate, but once you add it, it magically supports piping. Is that clear? No.
Yeah, makes sense now. Thank you.
Yeah, and there's of course a lot of this, so things should be done exactly as here, like you have this ampersand, and a lot of kind of syntactic noise, but yeah, that's kind of a more error-proof way to define this. And this const expr and friend, yeah.
Okay, and you mentioned that that data flows through the pipeline. So I guess one by one,
Yes,
one item at a
once.
time. So who actually holds this data? Is it the view?
Yeah, so you're right on the spot. So I'm gonna talk about. Okay, I have another chapter about debug, but then I have a chapter about this ownership and how the data flows. So let's. Do you want to go to that chapter first, or let's?
No, it's okay. I'll wait for it.
Okay, so because as you write all this code, it's a lot of like boilerplate, and it's a lot of things that can go wrong, a lot of moving parts, and you quickly like stumble across incomprehensible template related errors, concept related errors. They can be very long. It's cryptic, like you can get used to them over time, but they're still cryptic, and you have to understand how to decipher them. So that's why like I put debug techniques first, because as you write these custom views, you most likely want to be able to make sense and debug. So this is kind of how it unrolls. So if you have this pipeline on top, this view2 is basically an equivalent code. So because this, as you've seen, this operator pipe, it does nothing but simply constructing a view of parameters. So you can see it's kind of read from not from top to bottom, but from bottom to top, kind of, or it's like inside out. So you start from a filter that takes like a previous pipeline ending with transform, and there's a second parameter. It takes this lambda, which is passed. So the filtering predicate. So this is like the previous pipeline, and then this is the predicate. Then the previous pipeline is this represented by transform. So it's a transform view, which again, it takes previous pipeline, which is this owning view, and again a lambda, which does the transform. By the way, transform is actually a map, like in most languages it's called map. So in Scala is it map, right? So it's basically map, yeah. So map has this function that does the mapping, and then this owning view is having a vector. So this is how you can, if you rewrite it to this form, in some cases it's easier to debug, because then the compilation errors the compilation errors that are produced, they will stop trying to confuse this pipe with a so this pipe is actually the same as logical OR, as a binary OR, not logical OR, but binary OR in C++. So if there's a compilation problem with this, like type problem, constness problem, or something, concept problem in this code, then a lot of errors will be kind of misleading and pointing to compiler trying to apply logical not logical, but binary OR operation to this object and failing, and it will contain like 90% of the output will be garbage. But with this syntax, it will be not trying to use this pipe, so it will be more kind of printing what has failed, and you can like dissect it further to smaller parts in this. So another kind of trick is to become familiar with static assert. And static assert is something that happens in compile time, so it accepts some expression, and it can be like it's usually a type assertion, so it checks whether some type is equal to some other type, or like maybe it's a dynamic type which is equal to some other type, or it's a it adheres to some concept which is adds some restrictions to a type. So think of it kind of like a generic type in Go. There you can have certain restrictions associated with that type, or like in Java. So, and those restrictions can be checked in compile time by using static assert. So in this case, you can check that, okay, what I implemented in my class is actually a valid, it satisfies the input range requirements, and like my view satisfies the view requirements, and there's a lot of these concepts that name kind of a bunch of requirements. And another use case for this is when you have this pipeline, so it has this big composed type, and we use auto to make the compiler kind of deduce this this type. So especially like in the first, so here it's more or less clear what the type is, but in the first example, it's not really obvious. So using this static assert, you can actually, it's a trick to print the type like at compile time. So when you compile, it will try to to cast this to a boolean. So, but it will tell you that, hey, like it's not possible to cast it to a boolean because it has this type, blah 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 blah, and this is a giant type. But it basically prints you the exact type. It will tell you basically, hey, like it's not possible to cast filter view of transform view of owning view of this lambda and this lambda to a boolean, and you can read the actual type from that. And this last thing shows an example of how to use a decal type and decal val utilities. So decal type is basically you can pass it an expression, like a C++ expression that returns some value, and decal type basically gives you a type of that value. So think like if you say decal type of 3, it will be an int. But then if you have an expression that you don't know the type, like this view, let's say, or a function that returns a view, it has auto is a complicated type, then you can use this decal type to actually ahead of time ahead of time kind of declare this type. So sometimes you want to pre-declare this type before it's actually used, and then maybe use this type in some expressions or the class. So then you use decal type. But then another problem that can happen is that in order to describe this expression, you kind of need some let's say you have a function that returns this type you want to declare, but that function accepts some input parameters which you cannot create out of like thin air, because this whole thing happens at compile time. It's not a runtime thing. So this decal val is a nice utility to produce such values out of thin air. Like you just say, okay, I need a timestamp range value, and you declare it like this, and it appears like out of nowhere. It's an opaque kind of value, but it has a compatible type, and then you can call a method on it, and then again, because you don't care about the actual value, it operates kind of in the type space. Well, I guess it's more of a C++ kind of magic, but yeah, it's sometimes nifty. So this next section is about zero copy and data ownership. So what we want in our input ranges pipelines, we want to avoid copies at all costs, because for performance reasons we want to just read the value and then transfer the value through the pipeline and until the final kind of destination place. And yes, we do it like one by one, but you can think maybe we can do it like page by page, but in any case we want to avoid copying the value. But moving the value is probably fine, because maybe because the cost of reading, the cost of like seeking through files or database is probably much more expensive than moving the value. Moving is simply just like copying pointers most of the time. But in order to understand like how you move the values, you first need to start from who owns the data in the first place, right? So in the first place, the data is owned either externally or internally. But if we own it externally, like and only use references, there's a risk of getting dangling references and extra copies, which we kind of want to avoid again. So one solution is to use what's called own in view, and it's a thing from C++23, but we backported it, and this basically owns the start point of the pipeline, it owns the initial range, and then you can be sure that that range, it kind of stays alive as the pipeline is iterated through. And there is one implementation detail about that, is that in order to use it, you have to make your range movable. And in order to do that, well, you can check it with using the static assert std movable. So this basically is, if it compiles, it means everything is fine. If it fails to compile, it will tell you that, hey, your type is not movable, and it will explain you why. But one of the reasons why it can be not movable is if, for example, you use references. So in the bottom you can see this reader is a pointer, but before it was a reference. So the problem is that if you use references, by C++ kind of rules, a reference cannot be moved from, well, you can move from a non-const reference, you can move some underlying value, but you cannot move the reference itself. So kind of it's hard to yeah, I'm not able to fully explain just by this slide, but long story short, like the references, when they are created, they are kind of stick to where they point forever. You cannot like detach it from where they point, whereas with a normal pointer you can always detach, and you can it will contain a null value when you sort of detach it. You can always kind of reassign them, but references you cannot. So one simple solution is to change a reference to be a pointer. There are probably other solutions. So of course, changing it to a pointer might make some code less safe, but here, okay, we're making this less safe, but we're making the user code more safe. So it's kind of a trade-off. And the next example is, okay, we have this starting view that we own the data, And then how do we propagate the data through the pipeline so that we don't copy it, but only move the data kind of one by one. So I encourage you to pause the video and read the code and understand, try to understand what it does. So basically there's a vector. We start from a vector with objects of type A. And then the question is, and then in the transform function, we move the values out of the vector. And then the filter function, it filters some values according to the predicate. In this case, it doesn't filter anything. But then we basically, when we start iterating over the range, over the view pipeline, we print if, so in this object, it has a constructor and destructor, and if it's destroyed, it will be printing dead, and if not, it will print live. But hopefully it will print live. But the problem of this code it's that actually the objects are dead at this point, and the reason is that there's a problem with how filter is implemented, and this problem is stated in many videos. And people suggest basically different solutions, but like long story short, yes, so to quickly kind of explain what happens here and why the objects are dead at this point, is that filter it calls, so this lambda that calls move is called by the filter, and this filter it calls it twice, basically not once but twice. It calls it once to evaluate this predicate. Well, okay, filter is calling it once, but the second time it's called in the iteration. So sorry, so filter is calling it once for checking the predicate, and when it calls it, then it's already moved, so it's already kind of destroyed. And then the second time you call this lambda is when you start iterating. It calls it calls this lambda again, and it moves the second time. So this simply doesn't work. So I think it's kind of important to understand. Do you have a question about that, or it's not really?
Not right now. No. Oh,
No.
good.
So this filter, it is not caching the value. So when it executes this lambda, it simply basically asks, hey, transform, could you please give me your value so that I can call my predicate to evaluate whether or not I output you. And transform is giving him this move, and after the move the value is gone, it's basically destroyed and dead. And then and then filter is like, okay, you can have this value, yeah, just take it. And when you take it here, then it's already destroyed, and you move it second time. You call again this through filter, you call transform again, and it's second time kind of getting the value from transform, but at that point it's already destroyed. And the solution from ranges v3 library is to use a special utility view called caching, which basically if you put it after transform, it will remember the value, it will cache it. So in this case, you move it once, but then it will be kept in the cache until you move it. It will be available there until you move it, until some next code kind of moves it, and then again you perhaps need to add a second cache in your pipeline. And it might have some performance impact, but so far it seems okay, because because typically so moving is kind of cheap compared to the IO that we do. And then once you implement pipelines and once you kind of make it 0 copies, then you also might want to do some conditional logic to implement like full queries, because it's yeah, if you want a complex query, this pipeline, like single pipeline, is maybe too restrictive. So as an example of what you might want to do, something like this, where like you have ascending or descending, and you want to run different pipelines according to your Boolean, but there's there's a problem with this, that it will not work if you don't have const expr. If you just pass this ascending parameter as a Boolean here, it will not compile. And the reason is because those types, those compound types of these pipelines, they will be different types. So it's kind of like, think of it like as like the first return returns type A, but the second return returns type B. And then this auto, it has to be compatible with both A and B, but it's not magically compatible. So there's no such kind of automatic compatibility layer. And it will be, yeah, I wonder if this problem like happens in with Go generics. But basically this is not type erasing anything, so the type basically propagates up, so it has to be fully compatible. So one way to solve it is to use this template parameter, and const expr in this case, you basically at compile time decide whether to use the first or the second, but it's not always possible to decide things in compile time, and also this ascending parameter will kind of propagate to the callers, making the user code also templated. Another solution is to use what Ranges v3 library calls AnyView, which is a type erased version of Ranges. So you basically can cast any pipeline to a special type called AnyView, which is kind of, can think of it as a range of some element type, just any range. So kind of like an interface to all of the ranges, this AnyView. But yeah, so this might have some performance cost if you do that, but it should work as well. So kind of like std function type erases the lambda functions, then this AnyView can type erase ranges. But another solution is to implement like conditional logic using a special view. So in this example, we call it if view, and it kind of gets, it kind of does what you expect it to do. It simply accepts a Boolean, so it's just produces either this, the first or second, so it keeps both ranges, but when you start iterating, it will iterate over the first or the second, depending on the Boolean. But still, this solution has a bug, because if you look at this, the list is moved twice. So it means that if you move it first to be owned by this first pipeline, then for the second line it will be move after use problem. So it will be already kind of destroyed at this point. So the second pipeline will be broken. And here, yeah, there's a trick to avoid it. Yeah, and it's shown here. And I guess if you're a Scala person, then it might be familiar, but I'm not sure. Like so transform is what in Scala is map, and join is in Scala is flatten. So transform plus join is basically a flat map. And if you start with something with a single view, so it basically it contains one element. It's a sequence that contains only one element, which is a list, and then you kind of from that list you create. Well, if you just remove this range from list, but you can imagine that this produces just the same list, right? Because you return for this item, you just return a list and then you join it again. So you join all lists, but since there's only one list, it just becomes your original list. So is that like clear or not really?
Could you? I think I lost it a little bit. So could you try and do it one more time?
Yes. So you
I
flatten.
think I didn't have a chance to see what range from lists does.
Yeah, right. So but imagine this is just an identity function. So imagine this is, instead of range from list, imagine this is just a lambda that returns the same argument that it was passed to it.
Yeah, yeah.
So like it gets list and it returns list. So basically transform it, gets a value and produces a list. Then when you join, so this is a sequence of a single list, then this is a sequence of lists, right? After you transform. And then this join, it will flatten all this sequence of lists. It will flatten it to a single, concatenate to a single list, right?
Right, yeah. And sorry, why does the transform return a list of lists?
And well, not the transform, but the pipeline until transform. It will be a list of lists because because this lambda, it returns your list. So for each element of a sequence, you map it to a list.
Oh, right, I see. So almost like when you get one item, you would apply the conditional logic and from the if view, and that will give you one item essentially, but it will
Yes.
be wrapped inside a list.
Well, kind of. Yeah, I
Right,
guess
I see.
it's a bit more complex example, but again,
Yeah, yeah, no, okay, but I get it. Yeah,
yeah, if
so
you
it
forget
the
about range from list for a moment, and if you think about transform, just mapping elements of a sequence to lists, right? So
yeah,
then
yeah,
this range will be a sequence of lists, right?
yeah,
After the transform, and then after join, it will just concatenate all those lists, right? But then
yeah, got it.
it's only a single list from the start, so this concatenation kind of is tautological. It kind of does nothing. It simply, like, reformulates what how you do it, but at the end of the day it's just the same list as you started from, right? Because
Yeah,
it
yeah, yeah,
concatenates. Yeah, but with the only difference is that so you can either just, so this original list, right, if you, instead of this list, you can just put this if view, right? But the difference now is that the ownership of this list is contained within this single view. So therefore in this lambda you don't have it as an object, but you don't have it as a value, but as a reference. And then you don't have this problem of double move. So like here, so this whole thing, it produces you this desired range, desired list, or desired view, however you call it. But in this case, you pass it by value, so you need to move it here, and then it will be double move. But in this case, it's contained within the first single view, and then this one, it consumes it by reference. So this one assumes that the list is alive, the object is alive, and we kind of assure it's alive because because again the join reps transform and transform reps single view. So whatever you this whole combination, it inside it owns this list. So this ensures that there's like no dangling reference accidentally.
Okay, got that.
So yeah, and similar nature. So imagine that instead of like having full pipelines inside this if you, imagine that you actually call some function that returns you this range, and you call like one function here and one function there, maybe like f here and g there. Then the problem with this if view, and there's other views like merge view, the problem is that these pipelines, they are constructed kind of eagerly. So, but imagine that those f and g, that in order to construct a range, they need to do some heavy operations, like they need to actually, go to the database and open some cursors. So just creating that range is already like doing some work. But with this if you kind of don't want to do this work right here. You actually want to postpone the work until like you start iterating, because maybe if like the condition is true, you only need the first range, but if condition is false, you only need the second range, right?
Yeah.
So for this case, like you want to make this construction of the range to kind of be lazy, and for that we have a separate kind of utility called lazy range, which accepts a lambda function which creates a range, but this produces kind of a range that does not like it's instantly created, but it's created with a factory of ranges of a single range. And when you start iterating over it, only then it will produce the actual range, and that will execute the work that I was talking about. And this is kind of a nice utility, but if you even don't have this utility, you can simulate this again using this flat map trick. So on the top you can see this trick. So monostate is basically a void type. So it's basically nothing, like no data, no parameters, but it's like it's a sequence of a single void element, and then you pass it to this exec func, which produces a range from that element, and then you kind of flatten it, and it simply becomes whatever this exec func returns. So if it returns you a range or a view, then this result will be exactly the same view, with the only difference that this now is lazy because it will not call exec func until you start iterating. So is this kind of clear? Or
Yeah, I got this.
so it's kind of lazifying the loop, and of course this is a bit ugly, so yeah, so this utility is a bit nicer. Yeah, that's basically it. So I just have some references. So I recommend this YouTube talk, and there's this nice documentation page with pictures, and there's more talks, like starting from basic to more advanced talks. Yeah, the thing is that all these talks, there are some modern talks, but most of the talks, they are done by like developer advocates, or like actually the guys who are connected to the specifications, and so the implementers maybe. but not the actual users, because like I say, it's been like a long time since it was all specified. Like I can find blog posts which talk about this topic from 2017, but they talk like in the context of, oh, let's look at this cool library, let's like try some examples, but they are not actually, in 2017 it's not actually widely available to all the compile, like it's not even standardized, it's not even implemented, it's not like widely available everywhere. And so I think currently it's yeah, like I think what all those talks kind of yeah, they're mostly focusing on maybe design issues of the API and maybe just give some toy examples, but they there's no like comprehensive outline of all the like utilities you have to actually use in order to use this in Anger successfully. So I hope to kind of cover that gap here. Yeah. Do you have any more questions?
No, I think that's all. Yeah, it's been quite interesting to listen to this. Yeah, I liked the fact that it feels like views bring like some extra things on top of iterators, and one of the things that I liked about them is that they enable you to have composability, like you can compose many different things together, which is quite cool. I guess I was wondering, why did you decide to use ranges in your project? Like,
Yeah,
what was
like
the main selling point?
yeah, I'm like coming back to this, right? So I had a choice, like either I re-implement like something from scratch, right? Something akin to ranges, right? Because that's what the Go project does, or I just use ranges, right?
Yeah, yeah, and I guess
So
the
basically,
thing you
the
go from
ranges, they
ranges
support
was
this limit. For example, you use this in order to do limit. You call drop. No, you call take, right? So in order to, there's a take view which gets like a number of items and throws away all the rest. So you just call this take, or there's this page size. So for that there's a chunk view which basically does pagination. Then like for filtering there's this take while view, like it's like for the final kind of thing. And then there's reverse view, which felt like a good idea in the beginning. So it felt like it already implements a lot of kind of stuff that we might want.
yeah, yeah, yeah. It feels like it gives you like the tool set to do everything that involves moving data, transforming it, filtering it, and you don't have to worry about all this
Right.
boilerplate.
Yeah, like
You just
it's
focus on
basically like a
the
collection.
actual.
Yeah, it's like a
Yeah,
collection iteration API, which is detached from actual collections, but it works on top of like abstract iterator interface. But
yeah,
in Go,
yeah,
you kind of hand code everything from ground up. But here, the premise was that maybe we can reuse a lot of the standard library.
yeah,
But at the end of the
yeah,
day, it end up as a mix, right? You saw that we have to do all the tricks, plus there's a bunch of custom views that
yeah.
were.
It felt like it felt a bit like functional programming, and also like it reminded me a bit of the Stream API in Java as well.
Right.
I mean, probably has its underlying differences, but yeah,
Yeah.
it's cool.
Yeah, it's quite yeah, quite similar to that, I think. Okay. Any more questions?
No, that's all.
Okay,
Awesome.
great.
Thank you.
Yeah, thank you.